Okay, here we have lesson 11, free fall and terminal velocity. Before you go any further, I want you to go check that you've done lesson 3 and lesson 4. Lesson 3 is how to graph acceleration with a velocity time graph. We're going to be using some of that today. Lesson 4 was all about the idea of balanced and unbalanced forces. And in particular, we drew balloons and we drew the forces acting on helium balloons, whether they're the same or they're different. If you've got both of those done, then you can proceed. It might be worth having a quick look at the notes before you do this. So, free fall and terminal velocity. Jumping out of a plane or dropping any object on the Earth. Obviously, everything falls because of gravity. And gravity, if it had its way, would make everything fall at 9.8 meters per second squared. And if we lived on a planet with no atmosphere, you would get faster every second by 9.8 meters per second. But we live in an atmosphere, and so what we have is we have acting on everything that falls a certain amount of air resistance. So today we're going to be looking at what happens as an object falls and as it approaches its terminal velocity, that speed with which it can't get any faster. So I've made a PDF copy of this. It's attached to the lesson. If you want to print this off to fill out as you go, you can, or you can copy it straight into your book as it is. Now, this is usually a 6-marker question, and within this, there's loads of little questions. So if you can do this one, then it's guaranteed to help you in the future, whether it's about parachutes or it's about liquids and objects falling through liquids. So without further ado, let's give it a go. You make your jump, you decide to go. At that first millisecond that you jump, there is one primary big force acting on you. Now I'm going to draw my forces over here, and I've already drawn a dot. I'm going to draw the force, and that force is weight. Now, I've drawn the dots not in the same line because sometimes my arrows will crash. So acting downwards, we will have weight. Now straight away I can cheat because your weight during the fall is not going to change. So I can quickly paste the weight for each of these. I know exactly what they're going to be. Okay, and we can hopefully paste it again here and automatically done, and here. And the only way you would lose weight in the free fall is if you chopped a bit of your body off or you did a remarkably large poo, both of which I don't recommend doing during a free fall. So there's the weight. Now what's going to affect your speed is the air resistance acting upon you. So I'm going to do air resistance in red. So let's take part A. You've just jumped. It's a millisecond after you've jumped. Well, because the air resistance is a function of your speed. By that, go in the car, go slow, put your hand out the window, you won't feel much force. Go faster, you will feel more air resistance. So here, I'm going to draw the air resistance as small. I'm just going to put air res because I'm lazy. Okay, now if I was to put some numbers to this, this helps us gauge what the resultant is. So let's say the air resistance was 10 newtons, and let's make the weight 100. Keep it simple. Then my resultant from lesson 4, we see is what is left over when we take these two vectors away from each other. So we end up with a resultant force downwards of 90 newtons. And from lesson 4 we see if one force is bigger than the other, we use the phrase unbalanced. So it's an unbalanced resultant force. Now, if we have a force acting on a mass, we get an acceleration. F equals ma, Newton's second law. So if we were to now draw the axes for a velocity time graph, at this point here, we have a large resultant force. So I'm going to put T for time, V for velocity. I'm going to shrink it because I've gone a little bit too far, shrink it down. I'm going to copy it while I'm here. I think that failed. Try again. There we go. Okay, and I'm going to put one down there for in a minute. So, if we have a large force acting on a mass, then we're going to have a very large acceleration. And if you remember from lesson 3, a large acceleration, and I'll do it in purple, means a steep gradient. So, a large acceleration got near the end. A large acceleration equals a steep gradient. So now we've just got to repeat it for the rest. So let's have a look at the next one. You're getting faster. You can see there I'm drawing more little motion bits. So we're going to draw the air resistance getting larger. Still not as big. So this time my air resistance, air res, equals 70 newtons. That means my resultant force is now getting smaller. I had 100, I've now got 100 minus 70 gives me a resultant of 30. Still unbalanced. And so if we now go back to our graph, our acceleration is going to have decreased. And a smaller acceleration is a smaller gradient. So that's that one. Now, the key to jumping out of a plane is, well, 1, not to die, but 2, to reach your terminal velocity. And as you get faster and faster, your force of air resistance gets larger and larger. There will come a point at which your air resistance is equal to your weight. So we'll have 100 newtons of air resistance and 100 newtons of weight. So this is called freefall. You've reached terminal velocity. You cannot go faster than terminal velocity. So, resultant, 0. 100 minus 100 in vectors like this will be 0. If you have 0 force acting on an object, you have 0 acceleration acting on an object. So if I line that up, I can delete that. Now, it doesn't necessarily mean I'm going to go across at 0, because remember, this is 0 meters per second. In freefall, terminal velocity is around 130 miles an hour. So it'll be a straight line across like that. So I can put in here approximately 130 miles per hour. And that's for a human being. You may have heard the urban legend that if you was at the top of the Empire State Building or the Leaning Tower of Pisa, there it is, and you stood at the top and you threw a coin and it landed on someone's head, that it would go through their head and kill them. And it's not true. The terminal velocity of a 2p piece, for example, is about 63 miles per hour. And it's fast. It isn't going to kill you, though. It's going to hurt. So it's a heck of a shot if you happen to make it. But everything has a terminal velocity, and unfortunately, it's quite slow. Right, next one. You pull your parachute. You decide you don't want to hit the ground in a rapid deconstruction. So you pull your parachute. The aim of that is to massively increase your air resistance. So now my air resistance, when I pull the chute, I'm going to go for 250 newtons upwards. This is still 100 unless you've pooped yourself. And frankly, looking out of a plane, you probably want to. That means now my resultant is acting upwards with a resultant of 150 newtons. And again, I forgot to mention it here. I have unbalanced there. But here, where it was 0, I have balanced forces. Okay, So what happens this time to my velocity time graph? So let's make a copy, paste it in. Boop. And while I'm here, I'll do it again because I'm lazy. There we go. And let's take that out because that's not going to be true anymore. And go back to purple. So what's going to happen? Well, we're going to decelerate. And deceleration on a velocity time graph is a negative. I was going fast. I'm now working my way downwards. So I'm going to have a negative, like so. And the final one. When you come to land, you land at about 5 miles per hour. You do that because while you've had your parachute open, you are decelerating. And so you reach a new terminal velocity. So here's my air resistance. It will keep going down, and it'll happen quite quickly, until it gets back to 100 newtons. All the time you've been decelerating, though, to a safe speed. So you end up back with, and this is going to look familiar now, balanced, and zero resultant. So we have that, but this time that line has shifted. It's not 130 miles an hour anymore. It's down to here, 5 miles an hour, and it's not 130. It's about 5. So that is freefall from start to finish. There's loads of scientific words in there. Balanced and unbalanced. Resultant. Using Newton's second law, F equals ma, to explain the acceleration and the deceleration. Velocity time graphs. Understanding those. And all the way through, we're adding and subtracting, well, in this case, subtracting vectors away from each other. So this lesson builds on everything we've done so far. Now, to look at the big picture in terms of graphing, we can take all of those parts, A, B, C, D, and E, and if I draw now one large velocity time graph, I can draw the following. I'm going to choose purple. You jump at the beginning. Let me choose a thicker pen than this. There we go. You jump at the beginning. This is region A. You move to region B as you start, your acceleration decreases. You get to region C, terminal velocity. You can't get any faster. You then pull your parachute here, region D. You decelerate very rapidly, but then you approach a new terminal velocity. That curve is awful. Try that again. Nope, still awful. So we'll label this up. We'll label it region A, region B, region C, region D, and region E. And those correspond to these parts of my graph, but I'm just putting them together over the time of the entire jump. So you need to memorize that. In particular, note, this bit here, do not go backwards. Some people draw it lazily like waves. If you went backwards on a time graph, you're a time lord. And as far as I'm aware, none of you are. So don't go backwards on your graph. Trying to think of anything else I need to include for this. Nope. Now, what I would like you to do is, once you've copied that down, I would like you to actually describe in several paragraphs the forces acting and velocity changes in freefall. So this is a typical question I've seen come up a few times now. Used to be in the old one, and then it's been up once in the new type of exams. So all you do is you read it off. You take section A. When you first jump out of a plane, your weight is unbalanced compared to the small air resistance. This creates a resultant. A resultant force creates a large acceleration. Then you get faster. Your air resistance increases. The unbalanced force becomes smaller. A smaller unbalanced force creates less acceleration. You get the idea. So you're just reading each part off, putting it into words, and working your way along. If you do it correctly, you're looking at about half a page in your exercise book. I'd be really happy if you could do that. Please take a photograph and attach it to the assignment. Some people email me, and I'd rather you didn't. It makes it harder to mark, and it makes it harder to keep an eye on who's doing the work. If you know anyone who's not started yet, give them a poke. Tell them to get on with it. And I look forward to seeing a couple of you photographing the work and sending me in. Really cheers me up. Take care. Bye-bye.